Okay. Good morning, everyone. Howdy. We are, what is Wednesday today? Something was not tell you, forgot later maybe. Any question before we begin? No one? Okay. So as you know, tomorrow I sent an email yesterday or this morning. I forgot about office hours. I usually will have it 3 to 5. This week we have a conflict with the CVEN open house event, so I will anticipate 2 to 4. Okay. So as I mentioned in the email, I will be available on Zoom and also in my office if you want to come. So I will be connecting with Zoom from my office, so you can either connect or pass by. The homework is due, I believe I set up for Friday, right before class, like 12:30, so right before the beginning of this class. If you have any question about that, you can also email me. Okay, all right, so let's continue with our discussion. We have covered almost all the equivalences that we need to cover. I would ask please not to talk on the tables, thank you, because I can hear you to hear. Thank you. So we covered the equivalences up to the linear gradient, okay, which are all in the back of the book table. I guess that doesn't need to work. Thanks. The last one we still need to cover is another gradient. It's called geometric gradient, okay, which is not in the back of the book I mentioned last time because there is an additional parameter which is part of it, and it wouldn't be possible to put it in a table form. You would need a three-dimensional table to do that. Okay, and then after we discuss that, we mention the difference, an important difference, a very practical difference between nominal and effective interest rate. Yes. So the break. Sure, if I can do it like this. It's better, yeah. Oh, here it is. You tell me what you prefer. Is it okay? I can change it further. Huh? Just help. So I was saying after the gradient that we'll do in a minute, we'll discuss the nominal effective interest rate difference. And I will do at least a couple of examples, okay? So let me start first with the geometric gradient. That you see the slide seems scary with a lot of numbers and formula, but as I mentioned earlier, I won't really test you on these complicated derivations. Actually, they're not that complicated, to be honest, but I won't test you that anyway. Nevertheless, I need you to be able to recognize the associated model over which the equivalence is built on. And as you remember, we did the linear gradient last time. The linear gradient looks similar, but is actually different because the linear gradient, let me put it down here, it was the equivalent P, and then there is the 0, and then you start with the G to G and so forth. Remember, we did that last time. Okay, you might not remember, but whenever you do the homework, we do a refresh your memory. Here, even though the chart looks similar, we have a different gradient. It's called geometric because it follows a growth rate. Okay, rather than having a equal step G incremented at every arrow, we are starting with a given value at the first arrow. And then the second arrow is calculated with this formula. Okay, so make it explicit right here. We have a growth rate G, which is going to be given. You can imagine that being like inflation rate, for example, okay, over which the arrow will be following the growth. And then A1 is given, and A2 will be your A1, 1 plus G. Okay, and then A3 will be your A2, the previous one, 1 plus G again. Okay, and so forth. So in general, you can combine this growth equation with this generic formula. So every arrow part of the gradient, which is different than the first one being A1, will be calculated with this formula. A1, 1 plus the growth rate to the power of J minus 1, which is the year which, not the year, the period, sorry, better, the period in which the arrow is referring to is attached to minus 1, okay? In this case, it would be 1, and then A3 will become A1, 1 plus G to the second, if you do the math. It's consistent with that. Okay, so the equation that is provided and used to mimic these equivalences is derived here, okay? Once again, the derivation requires to consider every single arrow as a future value for which you do the straightforward transformation P given F of this plus P given F of the other, and you do that until the end of the series. You do your mathematical manipulation, you multiply everything by this factor, which becomes the original equation becomes the number 2. Then you do the first equation minus the second one, and we are lucky to have a compact relationship between the parameters. And this allows us eventually to get the resulting formulas, which, by the way, in this case, since we do not have the back of the book table, you're going to have to use your calculator to calculate the equivalence. Okay, we don't have that luxury to have the back of the book table. So there is an additional, let's call it complication here, is that I don't want you to get confused. The G is your additional parameter, which is still in the form of percentage, however, is something different than the interest rate at which you want to calculate the equivalence. Okay, see what I'm trying to say here? The growth rate only relates how this series of arrows will lay out, right? The I that we are used to know up to this point is still in the percentage over a period of time. However, it does nothing to do with the growth rate, okay? There are two different things, such as the I is your interest given by your bank, the G is the inflation rate, okay? They are both number in percentage, but they are two different things. If by chance, only by chance, the numbers are the same, could happen, okay? Then the formula, which is usually always this one, will reduce to this one. I don't get to the demonstration of that, okay? Actually, we reduce to even easier one. So the bottom line is, you can read this, but I will not ask you this, okay? You have to write down this to do your homework. And by the way, let me add, I know I will get this question. Should we memorize this equation for the test? The quiz? No. Okay, I will always give you the opportunity to have either a cheat sheet or provide you the formula. Okay, this is not about memorization. It's about being able to use the correct formula and put the right number inside to get the value. Okay, so whenever I ask you to do this equivalence, and now we see an example, if G is different than I, you just use this one. If instead you are in the odd situation where I and G are the same, you get this one for the equivalence. Okay, we are always trying to figure out to make it into context, assuming that I want to withdraw this series of arrows, okay, from period 1 to period n, and the bank is giving me that given interest, okay, how much I need to put in the bank right now to make sure that we'll be able to withdraw all this desired amount, okay? This is the concept. It's not always a bank problem, okay? But I am explaining that in this way because you probably understand it better, okay? Are you with me so far? Okay, hopefully, any question, any doubt? Let me give you an example of this. So I don't know whether I give you the example in the draft PDF or not. In any case, if I didn't, I will post it later, okay? geometric gradient example. So also put into context. See as if you were yourself. Okay, assuming you get a job. Okay, you get a job and your salary, to make it easier, is $50,000 per year. Okay, so you assume, again, to make it easier, assume you get the money all at the end of the period. Okay, even if you don't make the assumption, you can make the end of the period convention to assume that. Okay, so the period one would be your first salary, and this will grow because of salary increase with an expected growth rate of 1% per year in the next 4 years. Okay, so you have something like that as your salary. You have 50K as your A1. Actually, don't put A1, just 50K, and then 50K 1 plus G. Then I make it longer just because I can't write there. 50K 1 plus G to the square. 50K 1 plus G to the third, and then one more 50K 1 plus G to the fourth. Okay, so this is what we are dealing with, and I apologize for my writing, which is not going to improve. Okay, so I cannot do that. That's why I give you slides for the most part rather than writing. Okay. Anyway, so this is what you have in your planned future. Okay, obviously in a simplified scenario. And then you say, oh, let's assume that I want to put 10% of my earning every year in my own bank. Okay, so you are doing, this is my salary. I want to put in my bank in year one, this is 1, 2, 3, 4, 5. In year one, 10% of 50K. And then 10% of 50K 1 plus G. Okay, and then you do the same for the remaining years. So every earning that you have in the next 5 years, you decided to put in your bank, okay, as a deposit. So 1, 2, 3, 4, 5. This is the present, 0 right now. The question is, how much you will have at the end of the year 5, assuming that the bank is promising you a 3% interest per year. Okay, you can definitely use the geometric gradient equivalence to do these calculations. Okay, obviously it's all here. So let's do it case by case. In the given case, the G, which is 1%, is different than the I, which is 3%. So we are in the first generic case. The number of periods of the geometric series is 5 because it goes from 1 to 5. What we know is that your deposit, the first deposit, will be 10% of 50K, so it's $5,000. So $5,000 is this error right here. And then what can we do with this? We know that this arrow, even though they are pointing down, they are following a geometric growth, right? Because it's, even if it's multiplied by 10%, the next arrow will be the previous value multiplied by 1 plus G, okay? So given that, what can we do? We can find, the first step is an equivalent P, which doesn't exist. We are only calculating the equivalence of this cash flow. The equivalent P can be calculated using this equation because exactly match the geometric gradient model we just did. Okay, so we can directly apply the formula, which is the same as the previous slide. You plug in the numbers, you put G here equal to 1%, and equal to 5, I equal to 3%, and also here 3 minus 1. You do the math and you get this value. This 23,000 more or less is the equivalent amount of money which is of the future deposits that you are going to do. Okay. Doesn't mean that you have this amount of money now. No, it doesn't mean that. It just means that that number is equivalent to the cash flow that you are foreseeing for the future. Okay, and this is good because with this we can find what we are looking for, which is the equivalent amount of money you're going to have in the bank 5 years from the present, okay, which is calculated with a direct F given P calculation. Okay, so the future value, this is was asking in the original question. If you do the math at 3%, because 3% is what the bank is giving you, is 27,000 more or less dollars. Okay, so this is a two-step process. Why we need a two-step? Because we don't have a direct formula that transforms equivalently this cash flow to the future amount in 5. We need to do it 2 steps. Okay, you guys with me? Did I go too fast? Yes.
How is that accurate? That it's like if you deposit X amount of money over 5 years, it's like you gain different interest than if you deposit $23,000.
That's what the equivalence come in place. The equivalence exactly match those. Yeah, absolutely matches. Now I'm not going to do the counter proof, but if you want, you can certainly do it. You can consider this exact amount and calculate the interest, for example, 1 by 1. You do a F given P plus F given P plus F given P. You see that it matches exactly this number. So, of course, assuming that I is constant, G is constant, these are all needed assumptions. Okay. As soon as the interest change over time, then everything is changed. Okay. Any other question? I mean, other than the number itself, which obviously needs to be double checked if you want to, it's just the process that you want to be able to understand. Okay, most of these equivalences will be in need of you to do a double equivalence. Okay, not a direct calculation, but a couple of 2 steps like this. Okay. Now, let me do the second case. Let's assume that the interest rate, actually the growth rate, rather than being 1%, is better for you. They give you a raise of 3% per year rather than 1% per year. Okay, so pretty much it is coinciding with the interest rate that the banks give for your deposit. What is going to change? First, you cannot use the formula here. Okay, however, you need to use the second one because we are in the case where I is equal to G. Everything else is unchanged. So it's actually even easier because instead of this, you use this easier formula. Things are changed because the growth rate is more. So you actually get more money. So your deposits are bigger, right? So your equivalent present amount of money will be a little higher than before, and therefore also the future amount of money. Okay? Intuitively, it's exactly what you expect, right? You get higher raises, 3%, your deposit will be higher, and your future amount, your bank will be higher as well. But the important thing is that how to do these calculations, okay, for the purpose of this first part of the class. Okay, so that was the geometric gradient. One thing that I failed to mention, I was about to, but then I got distracted, I guess, is that there is an important difference. I want to highlight that between the linear that we did last time and the geometric that we just did, is that the linear start with 0. Remember I said that more than once? So it does look that we have a gap of 2 periods of the equivalence. That doesn't happen for the geometry. The geometry, you have the equivalency calculated exactly 1 period before the first error. Okay, so there is no gap, no apparent gap.